Awesome, thanks. Hi everybody, I'm Hart, and today I'm going to be talking about a non-standard variant of learning with rounding with polynomial modulus and unbounded samples. So this talk is going to be probably substantially more theoretical than most of the talks here, but I promise to try to keep you awake and make sure you're on time for lunch. So let's get started. So today I'm going to go over a deterministic variant of learning with errors that has both properties of unlimited polynomial queries and polynomial modulus. So the protocol and assumption I'm going to be going over today are inefficient, a bit complicated, and difficult to use in cryptographic protocols, although you can if you really want to. But this is potentially an important result that can help us to understand the hardness of learning with rounding, which has none of these efficiency drawbacks and is both maybe imminently and eminently practical. So for a brief outline, I'll go over learning with rounding. I'm going to talk about this new primitive learning with lattice rounding. I'm going to go over a few lattice tricks I use to come up with the final results. I'll present the main results, and then I'll talk about future work, which there is a lot of. So let's get started. I think the previous speakers have done an excellent job of introducing lattices, so I don't want to go too into details, but this is essentially the lattice notation that I'll use for the talk. And kind of the first new thing I'll introduce is this rounding notation. So this is what we call the round P notation. We take a vector or a number in ZQ and map to ZP. And what this really means in words, and how you can think of it, is we take something, we round to the nearest integer multiple of Q divided by P, and then we divide by Q over P. So that's basically what this rounding notation means. So now with this in mind, we can define our assumptions. So this is the LWE assumption, which I assume everyone here, or most people here, are familiar with. And we can also define the learning with rounding assumption in a similar way. Basically, the only difference between LWE and LWR is that in LWE we add noise, in LWR we use this rounding operation. And I should say that on the slide I have the keys and samples drawn from the uniform distribution. In practice, we can vary those distributions a little bit and still have hardness. So why should we study LWR? Why do we care at all? So I'll pose a question. What if the rounding interval, Q over P, was roughly equivalent to the maximum noise size of an LWE instance with respect to provable security? And what this basically means is if we had an instance of the problem with about the same security where the number of bits sort of rounded away are the same as the noisy bits. And you can kind of see this in the diagram on the screen where I'm rounding to the nearest multiple of 8, and my noise kind of has magnitude of about 4 on either side. So how many of the proposed NIST CAM protocols would still use LWE instead of LWR? So I don't know the answer to this question, but a lot of people in the room might. And it might be the case that a rounding protocol might even win the NIST competition, in which case we really need to study this assumption more. So there are a lot of advantages to using LWR instead of LWE. I've alluded to some of them, but the biggest one is that there's no need to sample noise. This inherently means that LWR is faster than LWE. It turns out it's also more resilient to side channel attacks because it turns out implementing noise sampling in a side channel invariant way can be quite difficult. The full determinism helps in other ways too. It enables some interesting theoretical applications, and it can be easier to work with. Like an adversary that can somehow repeat queries can't really gain anything from an LWR oracle. There are some disadvantages though. The main one is the security proof. It's much worse than LWE. There's a lot of slack. And there are some other minor analysis issues. Generally, it's easier to deal with Gaussian noise than rounding errors. But if you're truncating your noise anyway, you might run into these. So I think this is relatively minor compared to the security proof issue. So if I can convince you of anything today, even if you don't remember what I'm talking about. Hopefully you'll leave believing that rounding is an important problem to study in post-quantum crypto. So let's go back to the beginning. The original learning with rounding assumption was developed by Banerjee, Pikert, and Rosen in a 2012 Eurocrypt paper. I stated the assumption exactly. This is the same as before. I want to discuss a little bit about the security proof. So this is sort of the core idea of the proof. It's a little more complicated than this, but this should give intuition. And we'll sort of explain a lot about the rest of the talk. So the security proof idea in this paper is to start with an LWE sample. And then we're going to round the second term. And then we're going to hope and pray that the rounded LWE is the same as the LWR. And if this is the case, then we can just pass it through in a reduction and we're happy. However, that's not a good strategy in cryptography. So we're going to set our rounding interval Q over P to be super polynomially large so that this happens with high probability. It's slightly more complicated to prove, but that's the basic idea. And it turns out this potential one-bit rounding error is a source of a lot of problems with respect to learning with rounding. So recently there have been a lot of papers that have improved learning with rounding, and I'll throw up some parameters. A lot of these schemes have other nice properties besides the modulus improvement compared to the initial paper, but I'm not going to focus on those today. And in general, the main idea of these constructions are to cleverly leak information about the secret and noise without totally compromising security, or use some very, very smart statistical analysis to avoid instances where the noise changes the value of these rounded LWE samples. But as you can see, all of the moduli depend at least linearly on the number of samples W. And this even hurts practical protocols like key exchanges, where W might be the lattice dimension because you need a square matrix. So I'm going to go ahead and say this because I don't want to have to repeat this table later in the talk. But with some complicated techniques, we can get a modulus that's kind of slightly bigger than BP, which is essentially the optimal modulus for an LWE reduction. But our protocol is very clunky and very inefficient, and you'd use any of these in practice before our protocol. So, well, how can we improve this? How do we solve this problem? If you recall, our main issue is when our sample AI with dot producted with the key lands near this kind of rounding boundary, so an odd multiple of Q over P. There's a chance that adding in the LWE noise might move our output value across the rounding boundary. And so I've got this illustrated in this diagram here. We have a value for AI.S and a Gaussian distribution of where the point might end up. You can see if the noise is too negative, then we've changed the rounding value, and so we've kind of broken the reduction. So in other words, this property doesn't hold. So a first idea is, what if we throw out all tuples within B, which is our noise bound, that's how big our noise is, of our rounding boundaries. So in this case, right, we'll never make a rounding error because we won't have any points that are kind of close to this boundary. So it turns out this still doesn't work. Depending on the noise drawn for certain samples, we may or may not reject particular AI.S's, and this breaks determinism. And so here's kind of a diagram of what's happening. So we have this value of AI.S. If we sample a deeply negative noise term, then we'll reject this. Otherwise, we'll keep it. And this is really bad for certain applications where queries can be repeated. Because if I get to repeat this query enough times, I can determine with high probability exactly how far I am from the boundary. So new approach. What if an adversary could not tell whether a potential output point was close to a rounding boundary or not? So in this case, we could maybe throw out samples and get away with it because an adversary couldn't determine what we were doing. So the core idea here is to group M LWE outputs into groups. So we're going to take essentially vectors AI, turn them into matrices, and we're going to round these outputs to nearby lattice points of a hard lattice. And we're going to call this lattice rounding. So this is essentially what this looks like. We have a point, we round it to a nearby point in a hard lattice. So more precisely, I'm going to define lattice rounding in this way. It's going to take a vector x in the right dimension, a matrix B, a lattice lambda B defined by B, and a rounding algorithm that may have secret information. And it's going to proceed as follows. So we're going to round x to the nearest point. We're going to solve for u such that little b equals big BU, and then we're going to output u. And some comments on this. So in our paper, we use a slight modification of the trapdoor sampling and algorithm in the Michiaccio-Peikert framework, but there's nothing in particular that says this is the only way to do it. There are potentially many different ways to round. Again, I want to point out we may not get the exact closest point. This is a whole other discussion. And we output u instead of b. This is probably the most common question because, well, if x is random, then u is uniformly random over zq to the n. And in many cases, it's much more useful to have a uniformly random vector than a uniformly random lattice point. So moving on to the main assumption, or one of them actually, let's talk about learning with lattice rounding. So now, instead of learning with rounding, well, we're going to group samples and round to a lattice. So same basic notation, same basic idea. Should be pretty intuitive if you're comfortable with learning with rounding. But unfortunately, we don't know how to prove hardness of this assumption from LWE with polynomial modulus. This is still, I think, an interesting open problem. And the main issue is, well, kind of a problem that anyone who's tried to do a lattice proof has run into. We don't know how to simulate a rounded point in, or excuse me, a random point in space, and its rounded nearby lattice point without knowing too much secret information, like a basis for lambda b or some kind of trapdoor, essentially. So what do we do? Well, we're going to hack the lattices and get something. So again, this is our main problem. So our first kind of hack is we're going to cheat and only pick AIs such that AI.s is close to the lattice to begin with. Then, we can simulate, we can round. There are a lot of good things about that. So we're going to sort of change our sampling procedure. And in fact, we're going to get even greedier. So to set AI, we're going to sample a vector v uniformly. We're going to sample noise. And we're going to sample AI to be a random solution to this instance. And as you can probably guess, this means that AI is going to actually look random, and we can show this essentially directly from LWE. But this still isn't enough. We still don't know how to handle the simulation, even given these sort of cheating AI samples. So finally, what we're going to do is we're just going to make the modulus an even number and output the final value modulo 2 instead of the whole value. So we essentially add this mod 2 to the output. And well, this is finally something that we can prove hard for a polynomial modulus. So a couple of proof techniques that go into this that I kind of found interesting were, well, this first one called reverse LW. I called it that. It may be used somewhere else in the literature as something else, but if you recall, this is kind of regular LWE in the order that things happen. For reverse LWE, what we're going to do is we're going to sample an output, sample a noise, and then choose a random AI such that we get this output with this noise term. So we're sort of starting with an output and finding an AI rather than the other way around. It's easy to see that the outputs are statistically close, and this technique can be used to let us essentially more efficiently use non-uniform outputs from the problem, which is helpful when we're trying to tailor-make these AI terms, like I mentioned in the last slide. Another fairly simple technique that I'm pretty sure has been used in various different forms all over the place is just lifting the modulus. So if we have a regular LWE instance, well, if we double the modulus and we sample the key from this larger space, we can have this problem, which I've called here lifted LWE, which is essentially the same problem, except that we now can leak S mod 2. So we can leak a little bit of information about the secret and still have security. And you might guess that this is very relevant for our being able to output the solution mod 2. That would be correct. And so this problem reduces fairly simply from standard LWE. And this has been used essentially many times over in kind of leakage resilient literature around LWE. So the main result is this statement right here, that if we sample uniformly random S, we sample square matrix samples AI from this distribution that's dependent on S, we lattice round AI.S using the rounding algorithm A, then we get something indistinguishable from random. And the neat property is we get both a polynomial modulus and unbounded polynomial number of samples. So in conclusion, I'd like to say that learning with rounding is a very interesting, even theoretical problem, and it's got a lot of practical applications. I encourage people to study it. Some other favorite problems, sort of related in this space, are what's the hardness of LWE with the small number of samples and also very small noise? I think this is both interesting from a very theoretical and practical perspective. And this involves essentially improving the Michiancio-Peikert framework around this problem. PRFs from polynomial modulus LWE are a favorite pet problem of mine that's still unsolved. I think analyzing the learning with lattice rounding problem is quite interesting. And I don't have this up here, but I think that doing reductions between polynomial ring LWE and module LWE might be able to borrow some techniques from this area. So that's about it. Thank you for your attention. And if you have any questions, I'd be happy to answer them.
Thanks, man.